Okay, so this scientist is going to put things in a flask. The temperature is recorded. I forgot to sort of push record earlier. So the temperature is recorded because, why? You tell me now. I've already told you. Okay, so if this was a solubility, this isn't a solubility though, but if we use solubility as an example and how a high K means it's highly soluble, I get lots of ions. Low K means low solubility, I get a few ions. And so K, but you know if I increase temperature I can get more to dissolve. So K must depend on temperature because how much dissolves depends on temperature. So that concept applies to more than just solubility. That concept about how K is temperature dependent applies for any equilibrium constant. So it's always stated, the temperature is always stated, because if it was a different temperature, it would be a different K value. So then I can ring Germany and say, hi, I found the K value for this, it's this. And they're like, really? Because we did the experiment and it was this. Let's both do it at 200 degrees Celsius and then compare our results. Because you've done yours at 100 degrees Celsius and I've done mine at 300 degrees Celsius. That's why our K values are different. Okay, so every time we have to state the temperature, otherwise we can't compare results, we can't compare K values. So this temperature is nice and hot so that everything stays as a gas, and most like an ideal gas, the hotter the temperature. And they're going to take H2 and I2 and exist in an equilibrium with two HIs it's going to form.
Junior clock change.
Scientists are going to do this 3 times. The first time they do, that was not a straight line. The first time they do it, they're going to do it just like Science 10. They're going to put some H2 in the flask, they're going to put some I2 in the flask, and the H2 and I2 are going to make some HI. Fine. And the rate in which eventually it's going to reach an equilibrium, and the rate in which it's making HI is the same rate in which it's decomposing HI back into the elements. So we get a formation and decomposition happening at the same rates, because that's the definition of equilibrium, right? The forward rate equals the reverse rate. So forward and reverse rates happening, but at first I've just added these two. All right, so what's my KEQ expression from what we learned yesterday?
Products over reactants.
Okay, so tell me what that is in this case.
It would be square bracket HI.
Good. The power of 2 because of that balance divided by?
Square bracket H, 2, and then square bracket I2.
So it's the concentration of HI squared divided by the concentrations of H2 and I2 multiplied together. Okay? So that's the expression for this equation, for this chemical reaction. What are the numbers? So at equilibrium, so I put it all together, it makes some HI, makes a bit too much HI, that starts to decompose, and it eventually reaches an equilibrium. Okay? So this equilibrium that's happening is nice and stable. I know it's stable because I've run it for about 3 days now. I've got to wait for the weekend and come back. So I'm assuming it's reached equilibrium now. And this concentration never changes. Okay? So now I know it's reached equilibrium. Does that make sense? So kind of think of it like a big bathtub, where at first they splashed everything into one end of the bathtub, dumped a whole bucket of H2 and I2 into the one end of the bathtub. And all that did is form the HI by splashing over this way. Oop, too much. So it decomposes into a bit of H2I2, but not as high. Oop, too much. Then it forms some more HI, right? But it's not as high last time. So if you imagine the bathtub and I dump it into this end, it's going to go splosh, 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 until eventually you leave for an hour, you come back, and your bathtub is level. Yes? But don't you know there's underneath that a convection current happening, right, from physics? The hot water is rising, the cool water is going, right? So there's a bit of a convection current happening in your bathtub. So there is movement, dynamic, happening even though it's reached an equilibrium height level. Does that make sense? So I really like using this bathtub analogy, and I'm going to use it throughout this unit to help explain equilibrium a little bit, because it gives us something to visualize. So, splosh, 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 but I've come back in an hour and everything's stable. So what is the KEQ number then? What is the KEQ value? Well, I just plug in these numbers that they've given me. 1.56 squared divided by 0.22 times 0.22, or 0.22 squared, really, right? And so you tappity tap that in your calculator, and what do you get? Somebody's done it already? Nikita, are you going to be my calculator king today?
No, my calculator got.
But wow,
I don't know how to use
not
this.
so much of a king. I'm eliciting a coup here. Would somebody else like to please take reign?
32.2.
Pardon me?
Oh,
Say it again.
32.2 liters per millimole,
Liters per millimole. Liters per millimole.
because we have millimoles.
Oh, very good. Millimoles per liter. Sure, we'll take that.
Do you want the point?
Are you sure your units are liters per millimole?
Pretty sure, because one of them counts as that, no, the other one. Oh, it's squared, no mind.
There should be no units to this K value.
Alright, so then.
And
That answer's wrong.
I'm
too.
also
That's
questioning
squared.
about
That's squared.
I got
the 32.
Yeah, we both got
Right,
it
I
squared.
agree.
Okay, another
Yeah.
coup is happening. Dana, you're our new calculator queen. Let's see if the women can be better than you.
50.28.
Pardon?
50.28.
50.28.
There it is.
Really?
There you go.
Yeah.
Yeah, that's good.
Yeah, that's
Okay. And no units because moles per liter squared divided by moles per liter squared, they cancel out. Everybody understand the units? Raise your hand if you understand the units. All are canceling out. Okay, good. All right. Okay, so and at 448 degrees Celsius because that matters. Okay? Happy? Make sense? Okay, so let's figure out for situation 2. So for situation 2, they put a bit of H2 in there and a bit of I2, so splash splash from this end of the bathtub, but at the same time, they've put some HI in there in the other end of the bathtub. So they've dumped to both ends of this equilibrium system. They've initially put this and this, which are going to form this, and they've initially put some of this, which is decomposing, all at the same time. See that? And splosh, 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 eventually it reaches the equilibrium. And so what are those equilibrium constants? Does my expression change?
No.
Nope. So I just plug in some new numbers here. So now I'm done with trial 1. I'm looking at my second flask where I have 2.10 divided by 0.30 squared and squared. Pardon me, Nikita, who wants to come back? Pardon?
49.
Really?
Yeah.
Agreed? Taylor? Okay, let's look at number 3. So the third situation is they put nothing of H2, nothing of I2. Karen, could you start writing this stuff down? But they start with HI. Okay, does everybody get that? So no splash splashing this end of the bathtub, but splash splashing that end of the bathtub. And they chuck it all in, and again it splashes this way, splash, 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 until it reaches an equilibrium. And at equilibrium, and I'm going to have to scroll down, so I'm just going to write it here for fun, is going to be 2.50 squared divided by 0.35 squared. Notice how we produce the same amount of H2, I2, right? H2 and I2 are the same amount if we've started with the same amount. This is going to come into play later on today. If this starts with the same amount, this ends with the same amount here too. Here I've started with the same amount, here I've ended with the same amount. See that? Start and end is the same. That's going to play a factor for us later. Okay, so tappity tap.
51.
51 at 448 degrees Celsius. Can you see that these values, the 51, the 50, and the 49 are all considering this is an experiment, these aren't theoretical, these are practical results, pretty close. Why? Because K is a constant. It's a constant. It doesn't matter what you put in the bathtub. The rate of the forward and the rate of the reverse will always be the same. The level of the bathtubs might be different. The height, the concentrations might be different. But how fast that convection current is happening in that bathtub is the same in every situation. Okay, so the rate of the forward and the rate of the reverse are going to be the same every single time I reach equilibrium. The height of the bathtub is different, fine, but the rate is the same. Make sense? It is a constant. If I change the temperature, now I'm going to get 60 or 41, right? No longer constant because I've changed the temperature. But as long as I keep that temperature the same, each of those K values will be the same. Jordan?
So the reason why these values are just slightly different is due to like a little percent error?
Correct.
Yeah, okay.
Correct. Does that make sense, everybody? Okay, so that is what K means.